Good morning, everyone. In today's class, we'll be going through the calculation of no load current in a transformer, right? So, as we know by basics, that no load current I naught, okay, which has two components, okay, so which is one of them is the IM, that is usually known as the magnetizing current, right, and the IL, that is the loss current or the loss component, right. Therefore, I naught is equal to square root of IL square plus IM square. Okay, so this is the basics that we have, right. So therefore, if you want to estimate the value of I naught, that is the no load current, right, then it will have to have the values for IM and IL. Okay, so this is how we will be trying to find out I naught by IM and IL. Okay, so we'll see for single phase transformer, right. So for single phase transformer, right, so this is the diagram that we have. Okay, so here the important part is, right, the Ly, right, this is the Ly, right, and the LC. Okay, so these two are the components that we must be knowing. So what is LC, right? So LC is the length of the flux path through the core. Okay, this is the core that we have. Okay, so the core LC, it is the length of the flux path through the core. So it will be equal to HW, that is the height of the window, this much. Okay, next we have Ly, this is the Ly. Okay, that is the length of the flux path through the yoke. Okay, Ly and Ly. Okay, so that will be equal to WW, that is the width of the window. Okay, next we have to know is total length of the core. Okay, it is 2 times LC, right. So 2 times, because we have 1 2. Okay, 2 times the LC, and total length of the yoke is 2 Ly, this and this. Okay, so that is why we got it. Next we want to find out the MMF, right. So first we'll go for the MMF for the core, and then for the yoke. Okay, and then we'll go for the amp turns in total. Okay, so for MMF for the core, MMF per meter. Okay, so MMF per meter for maximum flux density in the core into total length of the core. So it is MMF per length into length will give the total MMF. Okay, so that is what we're doing. So this ATC, right, it is nothing but the MMF per meter for maximum flux density in the core. Okay, so that multiplied by the total length will give us the MMF in the core. So it is ATC into 2 LC, because the total length of the core is 2 times LC, that is 2 ATC into LC. Okay, in similar fashion we will be finding out the MMF for the yoke, which is MMF per meter for maximum flux density in yoke into total length of the yoke, that is MMF per length into the total length will give us the total MMF. That is what we have. ATY, right, here this ATY represents the MMX per meter for maximum flux density, okay, in the yoke. So that is what ATY we have, and multiplied by the total length of the yoke, that is 2 Ly. We already have 2 Ly, so it becomes 2 ATY Ly. Okay, next. So now we'll have to have the total magnetizing MMF, that is AT naught. Okay, so this is a no load magnetizing MMF, which is MMF for the core plus MMF for the yoke plus MMF for the joints. So with this figure we'll see what are the, so the MMF in the core, MMF in the yoke, right, which already we have found out. Okay, and then the MMF in the joints, these are the joints, okay, where there is intersection of the yoke and the core, these things. Okay, there will be MMF here also, but we have considered only so much, right? But at these points where they intersect, that is the intersection of the core and the yoke, that is taken as MMF for the joints, right. So already from basic we have MMF for the core is 2 ATC LC plus MMF for the yoke, which is 2 ATY LY plus MMF for the joints as it is. So this will give us the total AT naught, right? So once we have the total AT naught, right, then we can go for the maximum value of magnetizing current. Okay, so it is AT naught by TP, right? So the turns, right? So ampere into turns divided by turns will give us the ampere. That is the maximum value for the magnetizing current is by this equation, that is AT naught by TP, right? But usually we go for the RMS values of the current, right? So this is what we are having, right? So AT naught by TP was the maximum value. Now we are finding out it for the RMS value, which is represented by Im, right? So it is AT naught by root 2 into TP, right? So if the magnetizing current is sinusoidal, right? And then next Im, that is the RMS value of the magnetizing current, is AT naught divided by Kpk into TP, right? Where Kpk is a peak factor, and this equation is for non-sinusoidal, right? So this is what we have already seen through when we are done for the magnetizing current, right? So we had differently studied for sinusoidal and non-sinusoidal, right? And again in we have with the concentrated and distributed winding, we get different types of waves. Okay, that is what is the same thing has been repeated. So I will be getting Im, okay, by these two equations depending on whether it is a sinusoidal magnetizing current or non-sinusoidal magnetizing current, right? Then I have the loss component of no load current, okay, IL, which is given by Pi by Vp, okay. So where Pi is the iron loss in watt, right, where Vp, right, terminal voltage of the primary winding, okay. So by this I'll be getting the value for IL, and as usual, right, by basic, I naught is nothing but Im square plus IL square whole raised to 0.5, that is nothing but I naught is equal to square root of Im square plus IL square, okay. So this is the no load current for single phase transformer. In the next part we'll be going for three phase transformer. Again here it is almost the same, okay. So with the same steps for what we have done for single phase transformer, we'll be going for the three phase transformer, right. So this is the three phase transformer, right. So the difference here is you can see three limbs, right. So now LC is 3 times. Earlier we had only 2, okay. Now we have 3, right, and Ly is the same, okay. That is what we have, okay, fine. So next, total length of the core is 3 times LC, okay. It is 3 times the core, 3 into LC, and total length of the yoke is 2y, okay, sorry, 2 Ly. So from this to here, right, that 1 Ly, and this to this, right, the top Ly and the bottom Ly, which constitutes to 2 Ly. Next, here LC is equal to HW, that is the height of the window, right, the similar we had in single phase transformer also, right, this much, right. Next, the change is here Ly, there Ly was WW, right, though, but here it is 2 WW plus D, okay. So why we have two windows, okay, this, right, plus, right, half of the D, right. So that is what we're having, right. So WW, 2 WW plus twice of half of D, okay, because here we'll be having our, right, the windings like this, right. So usually, right, so half of we take it, okay. So that is how we are getting. So it is half into 2, okay. That's why we are getting it as D, okay. Next, so again similarly, mmf for the core is equal to mmf per meter for maximum flux density in the core plus total length of the core, okay. That is what it is here, same, okay. So this mmf per meter for maximum flux density, it is 80C, right, into 3LC, that is the total length of the core. right? mmf per length into total length will give us the total mmf. This is for the core. Similarly for the yoke, right? So mmf for the yoke, we have mmf per meter for maximum flux density in the yoke multiplied by total length of the yoke. So it is mmf per length into total length will give us the total mmf. Okay, so it is aty, that is the mmf per length, okay, per meter into total length, that is 2 ly. So it is 2 aty ly, right, which is as much same as what we had for single phase transformer. So total magnetizing mmf 80 naught, right? The same equation, mmf for the core plus mmf for the yoke plus mmf for the joints, right? So here the mmf for core, which was 2 atc lc in single phase, now it is 3 atc lc. Okay, so that is what we are having, right? So we get that from this part. Okay, 3 atc lc. Okay, so that is there, plus 2 times aty ly, 2 times aty ly plus the mmf for the joints. Okay, so that is what we are having. Okay, so by this we get total magnetizing mmf, right? Now next part is the total magnetizing mmf per phase, that is 80 naught. Okay, therefore it is 3 times atc lc plus 2 aty ly plus mmf for the joints, which is the total mmf, right? That is the 80 naught divided by 3, because now we are having it for per phase. Okay, next similarly, so maximum value of magnetizing current per phase. Okay, it is now per phase 80 naught by tp. So we'll be going for, this is the 80 naught, that because it is per phase now. So this is the maximum value of magnetizing current per phase, 80 naught by tp, right? So similarly we'll be finding out the RMS values, okay, for the magnetizing current. Again we have two conditions for sinusoidal and non-sinusoidal. So for sinusoidal, right, Im, that is the RMS value of the magnetizing current, is equal to 80 naught by root 2 into Tp. Alright, and for non-sinusoidal, right, it is Im, which is equal to 80 naught divided by Kpk into Tp. Right, again where Kpk is the peak factor, okay, for non-sinusoidal. Right, so by this we can find out the value for Im. Okay, then the loss component of no load current, IL, okay, is equal to Pi divided by 3 Vp. Alright, so it is, since it is 3 phase, it is 3 Vp. Okay, where Pi is equal to iron loss, okay, in watt, and Vp is the terminal voltage of the primary winding. Okay, right? So the total iron loss for 3 phase, right, total Pi will be 3 times the iron loss per phase, right? So and then again by basic equation, I naught is equal to square root of Im square plus IL square. Okay, fine, thank you.